Okay, so the recording has been started. Let me share my screen. Okay. Mm, yes. And so today, what our objective will be, let's just start slow, and then we'll pick up as we go. Okay. So, welcome to week 2 of reinforcement learning course from IIT Madras. And yeah, I hope you have set up the Python environment, right? Um Yeah, so today's agenda will be so if you remember last time, right? Last time we did uh, your uh, like how to code Markov process and Markov reward process, right? If you can remember those programs. What we did, like let me give you a quick refresher. Uh, so Markov, what was the Markov assumption that like I have the next slide. Yes, this one, right? That like you don't need to know the entire history to predict the next state. Rather, you can assume that you can predict next state with respect to the current state. Okay, and the action. If you can take recent processes into account. But for Markov process and Markov reward process, there is no action. So you can assume that next the current state is a good predictor or a complete predictor of the next state. Okay. Now, where we left off is coding Markov decision processes, right? So today's agenda will be to learn Markov decision process, how to code it, and like how the transition dynamics is coded. And again, we'll look into the classification of RL. So this is very important, classification of RL, and some concepts like return, discount factor, value function. Okay, so this is the current setup for us. Okay, and finally, like if time permits, we'll go through numerical solutions from the previous year assignment questions. But what I saw from the assignment questions is like before solving them, you need to know some basic concepts like what is Q function, what is value function, what is this return, discount factor and all, right? Epsilon greedy policies and all. So my approach like with this course would be like this. We'll go in a pace that introduce you to the concepts like in a incremental fashion rather than directly going for question answering. Okay, and the assignment questions are not that like big, right? We can cover most of them in 1 week. So even if we, let's say in the initial 2-3 weeks we don't practice any questions, we can cover all of them in 1 week. Let's see if time permits, we'll do it today also. Um, but from the assignments question, what I observe is you need to know like like this return, value function, discount factor, all these concepts, Q function, before you can fully understand uh, the kind of depths of the questions. Okay, so maybe like in the week videos there are like there is like introduction to these concepts, but like from theory to practical how they are implemented, we'll see it now. Okay. So yeah, so like as you remember the RL setup is this. There is an agent that takes action to an environment. It gives its reward and a state, right? And observing those reward and state signals, the agent again take an action. Okay, so that's the RL loop. Yeah. And these are the world representations that we talked earlier: Markov reward process, Markov process, and Markov decision process. And the examples were, let's say, a gas transition, that transition from, let's say, uh, few states, right, with some probability. That's that's the Markov process. Okay, let's say for here the image is chocolate, vanilla, and strawberry, different flavor of ice creams. How they like what is the probability of transitioning from one chocolate state to another, like one ice cream state to another ice cream state. Okay, similarly if there is a reward, basically how much I like the chocolate or how much I like the vanilla or strawberry, based on that we get the reward function, right? And there is a scalar number, this gamma, right? So last time we haven't talked about this gamma. right? We just completely skipped that part. So today we'll see how this gamma or this discount factor actually uh, helps us to plan in future. Okay, and theoretical concepts with respect to reward processes are total reward and return. So last time I know, like I remember that we observed this total reward thing, right? We just added the total reward as we like unroll a particular MRP, and we reported that the total reward we got is, let's say, 56 or 63 or anything, right? And because this entire system is a probabilistic system, it transitions to different states is based on the like this transition probabilities. So every time this total reward would be different. Now the decision processes where you have actions. Okay, so actions can be anything. So in a grid world example, action can be like left, right, up, down, something like this, or for left, right, forward, backward, or anything in a, let's say, for example, in an environment where you are trying to learn how to land a rover to moon. That's a actual environment called lunar lander. um, your action can be, let's say, throttle or brake or push right, push left. All these can be your like actions. Okay, now what is the next, like, addition from MRP is this action state. Okay, and because of this action there is a new theoretical concept called policy. Okay, so what is policy? Policy is basically uh, a mapping from state to action. So in which state what is your action, or let's say in state 1 your action is A2, in state 2 your action is A3, in state 3 your action may be A1, like this. So policy is nothing but a mapping from particular state to a particular action. Okay, so yes, so let's code the MDP now. Okay, so we'll draw a grid world, not something like this. Let's say we draw a hypothetical grid world, and we'll try to like write a model for it, MDP. Okay, and I'll also give you a quick refresher on last week's code base. Okay, so yes, go to that. Week 2. Okay, so now we have this week 2 folder, right? Inside it we have, let's say, week 2, and I will just revise the last week's code once. So this was the MP Markov process, where we have states like CVS, and we have the transition probabilities like this: PTR S to C, C to C, C to V, C to S, then V to C, V to V, V to S. All these are encoded in a matrix, right? And then we have a state to classical mapping. So basically, in which state the current like environment is, right? So if it is in the C state, the probability of being found in a C state is 1. Then if it is in the V state, probability of being found in the V state is 1. And if it is in the A state, probability of being found in the A state is 1. Okay, Now what we do, we basically multiply this classical state with the PTR, then we get a next state probability matrix, right? Next state transition matrix. So these are the next state probabilities that we can transition to, and then we do just a random sampling from the state space and the next probability. So this gives us the next state. Okay, and now this is how we can transition in an MP. In a reward process, the only thing that changes is now we have a reward matrix, right? It can be anything. So for us, because we named the states C, V, and S, it is actually represented uh, in a dictionary. Okay, but if it is, let's say, numbered like 0, 1, 2, then it might be also represented in an array. Okay, and this state indexes will be the array indexes basically. So state 0 means it's in the 0th index of the reward array. So same thing. So we just compute the classical to so new like this ID to classical states, multiply it with the transition matrix, get the next state probability distribution, sample a next state from the probability distribution, get the reward for that state, add it to the total reward, and then let's say we transition for next 100 steps. Okay, so yeah, and then if it goes to 100 next steps, and finally prints total reward is 430. 430. Okay, so this was our MP and Markov process and Markov reward process formulation. Now let's see how a decision process is coded. Okay, and for that we'll not go with some kind of this abstract type transition, we'll rather go with a grid world. Okay, so MDP with grid world. Okay, and why we're choosing grid world? Because it's easy to understand the actions and it will be consistent across all the states. So every state would have 4 possible actions: left, right, forward, backward, or up, down. If I see uh, the grid world from a top view, the action can be left, right, up, down, right? So let's have a grid world then, and we'll choose a very small grid world. Okay, okay, so okay, I think this is okay. Now let's have a grid world. Okay, and this is a block state. So let me get the red one. This is a block state. So basically you cannot go there. Okay, so possible states are what? Actually you should write like, oh sorry, eraser. Yes, yes. So this is the 0th state, this is the first state, and this is the second state, and this state is basically it doesn't exist for us, right? Now let's say the agent, um, uh, let's search with an element, then search a mouse, right? And let's have this mouse here, okay, and a cheese here. So now you know the goal states and the starting state, right? So this is my world. Now we need to write what things we take. This is an MDP, okay? So oh, wait, tools. Yes, this is an example of an MDP. Now let's write the dynamics. So what are the things that we need to define an MDP? a state space S, a reward space R, a action space A, or let's just do the opposite, S A R, then PTR, probability transition dynamics, and then finally you have PTR, and then finally you have gamma. So 1, 2, 3, 4, 5. There are 5 tuples that we need to define to model this entire world. Okay, and what are the actions? So only we can go up, down, left, right. Okay, and let's encode these things. So states are already encoded to 0, 1, 2. Okay, now let's encode the action space into, let's say up is 0, right is 1, down is 2, left is 3. Okay, so there is 3 action space. Now let's write the, now we have enough, and this is the goal space, right? And our objective, so what is our objective? Objective is to find food as quickly as possible. Now given this objective, what should be our reward function? So I remember last time many of you have asked that who actually writes the reward function, right? So if I am defining the world, I would be responsible to model it for the agent, right? So I would be also defining the reward function based on my objective. So my objective is to find food as quickly as possible. So if it roams around in the other states except for the reward state, it will get a penalty, and penalty by reward function is known as some negative number. Okay, it can be negative 100, it can be negative 200. Okay, so let's not uh, like let's not choose a very high reward function. Let's choose only -1. Okay, so basically as long as you spent in this state, you get a penalty, and the next state will also be -1, and finally if I reach the goal state, I get a plus 100. This is my reward function. Now that is a very good case study that we may do later on after we have some more background on the topic, is defining how aggressively we penalize or how aggressively we reward the mouse. It shows different behavior. For example, like it's a very good area of research nowadays. Is, let's say if I penalize it too badly, right? If I penalize, like the reward is plus 100 at the end, and the each state is like -1000. Okay, and there is a dead state, like there is a state, let's say this one, uh, where the environment ends. This is where the environment ends. So see, going this way to the reward doesn't make sense for the algorithm, right? Because it will be -1000, -1000 plus 100, right? Rather than, if this is -1000 also, going to the dead state makes more sense for the algorithm. So basically it shows a suicidal tendency if I reward it very aggressively, like if I penalize it very aggressively. It doesn't go to the goal state, rather it goes to the dead state. Okay, and they like this, like how to reward the system. What is -1 here? -1 here is the reward function. So how much reward it will get in that state 0 or in state 1 or in state 2. So because this is a goal state, it's a positive like positive 100. But the other states, because the objective is to find food as quickly as possible, we are penalizing the mouse to stay in a state that is not a goal state. Okay, okay. So yeah, so there is a good case study that we'll do later on to see how this rewarding mechanism can introduce different behavior in the agent. So like if I let's say example, if I do a plus one here instead of a minus one, then and here also the environment ends, right? After reaching the goal, the environment ends. So going to here, the optimal path only takes you plus 1 plus 1 plus 100, means plus 102. Whereas if you just jump around these states 1000 times, you can get 2000, right? So that's another kind of reward hacking that the model can do. So if you do not place this reward function very properly, it can introduce different type of anomalous behavior in the agent. Okay, so for now we'll not look into this, we'll later do a case study. But for now let's just have it as minus 100. Okay, and the environment ends at here and it ends at here. Okay, okay, so let's write the state transition matrix for this. I'll write it in red. But how to find setup possible comment, but how to find the setup possible states and the action, because probabilities shall be right? That is like how to find set of possible states and possible actions, because probabilities shall be. Yes, we'll see how to actually write the probabilities now.
Not the probability, it is possibilities, because if we take the all possible states and the
Mhm.
possible actions, and if we consider I mean the all possibilities, so number of possibilities would be exponentially large. So
Yes,
how to,
exactly,
how to find the
exactly. Exactly.
probability?
So your this world models actually grow very large. Like as you increase the number of states, you increase the number of actions, the possible policies or possible probability transitions grow really like quadratically. Okay. So that's why we are going with a toy example. Okay, you cannot model a very big environment like as a model based method. So we'll discuss all these details later on. So for now we just want to see how to model an MDP. Okay, if I know everything, so because there is only three states, I can model it by hand. How? The state transition probability, what is this? This would be a set of 0, 1 and 2. Only these states are possible, right? And this is a block state, so we just completely ignore it for now. We can actually model it as if somebody goes in there, they gets a very high negative reward, and that's just do a self loop with high probability. We can model it that way, but let's not do it for now. Let's just only stick to 1, 2 and 3. Okay, this is just a block state, or you can think of it as a wall. Okay, okay. Now actions, what are the actions? Up, down, like we have already encoded it 0, 1, 2, 3. So 0 mean up, right, down, left, right? So we'll write like up, right, down, left. Now the reward function is basically a state to reward mapping. So because the states and things are like already marked in 0, 1, 2, we can just use a normal array or a set or a list even, right? So the reward function is -1. We'll change it actually later on. -1, -1, 100. Oh, sorry, 100. If this is the reward function, it's actually a function of the state S. Function of the state S. But uh, see the okay, shouldn't there also be a possible set of moves given the current state? Yes, yes. So there is a possible set of moves, but it will be considered in the probability distribution. So the action that is not possible in a state, let's say the right action here, right? It's not possible. So basically, it will contribute to the self loop. Okay, we'll see the like the probability distribution, then you will understand this. Yes. Okay. Now PTR, and let's say gamma. Let's just move that to the side. Gamma. Right? And gamma is equal to, usually it is like 0.9, and I'll tell you later on how, like why we choose 0.9. Okay, it's a really like cool reason why we exactly choose gamma as 0.9 or is equal to 0.99. This is it depends on how much future we want to plan. Okay, so probability transition dynamics. So now it's a bigger matrix, very big matrix of what? Of action cross state cross state. This is the dimension. Earlier for MRP, the matrix was only state cross state, right? Because there is no action involved. Now because there is action also, you need to have an action axis. So what does it mean? It basically means we have now, because there are three things and four actions, so it will be a 4 cross 3 matrix. Okay, so how does it look? It looks like this. 1, 2, 3. Maybe I need to wait. This one. Okay, and what does this tables mean? So this is the up. If you take up action from all the states, okay, if you take the right action from all the state, if you take the down action from all the states, and if you take the left action from all the states, and these are basically same: state 0, 1, 2, state 0, 1, 2. So let's write the probabilities now. So what are the probabilities? So we are at this state. Okay, we are only taking up. So 0 to 0 probability. What is the probability of being taking up and staying in 0? It's a 0, right? You will always go to this one state. So the probability of being in one state will be 1, and then other state will be 0. Got it? Now you are in the first state. You take up. So you will basically hit this wall and again go back to the same state. So from 1, if I take up, the probability distribution should be like this. It will do a self loop. And from here, if you do an up, it will also be a self loop. So 0, 0, 1, right? Because it will basically hit a wall, hit this wall and come back to the same state. Okay. Now let's fill the right. So can someone just tell me what will be the right transition dynamics? So let's write 0, 1, 2. This is 0, 1, 2, and we are taking right action, right? So we are here in the 0 state, taking right is basically we are hitting a, yeah, we are hitting a wall, right? So we'll go back to the same state. So 0 state only. So 1, 0, 0. Yes, Vijay. So it's 1, 0, 0, and the second row, we are here, we're taking a right action. Will be in the goal state, right? So 0, 0, 1. And finally, if we take from here to right, we'll also hit a wall and come back to the same state. So 0, 0, 1, 1. Similarly, we can also fill in this D and L. So let me fill it quickly. Down. So we'll only stay in the same. So 1, 0, 0. Then from there you go back to the 0th state. From there you go to the, like you hit the wall and go back to the same state again. And finally for the left operation, you go back to the same because you hit a wall Then here also you go back to the, sorry, go back to the same because you hit a wall. And the last state, if I take a left here, I'll go back to the 1 state. So 0, 1, 0, 1, 0, right? So this is my um, this is the probability transition dynamics for an MDP. Okay. Now we can model reward as a function of state. Obviously, you can model reward as a function of state, but reward has actually two models, and you can choose whichever you want. So reward can be a function of state, sorry, state, or reward can be a function of state and action. Okay, or reward can be a function of next state, right? Basically this wherever you land, that is your function, right? And so if I just follow the Markov principle, from a state what action I took land you to a certain state, that gives you the action. That like the from a current state you take some action, you go to a next state, that gives you the reward for that state, right? So in most RL literature, instead of modeling it as plainly as a function of state, what we do, we also factor in the action component. So given a state or action where you transient and you get the reward based on that state. So instead of going in this formulation, what you will do, and that was the valid MRP representation, right? So for an MDP, the reward representation is little bit more complex. Reward would be same, a big matrix with safe, but action cross state cross 1. Okay, so basically it's because it's only one value, right, on a scalar value, action cross state cross 1. So it looks something like this is for one action, 2, 3, 4. Now same actions up, right, down, left. We put the values, let's say these are 0, 1, 2, right? So you from 1 you take up, where you land, from 1, like from 0 you take up, you land in a non-goal, like not goal state, so it will be a -1. Same from 1 to up, you get self loop to the 1 state, you get a -1. From 2 to up, you go self loop to the same state, but you get a +100, right? +100. Let me +100. Now again, if I go for the right thing, uh, from the 0th state you get a -1 because you hit a wall. Now from the first state you go to +100 because you reach to the goal state. From the goal state you go up +100. From the down call, what is it? For the down it will be -1, -1, -1, and then +100. 100. And now finally for the left call, it will be -1, -1, -1. Why the last one is -1? Because if you take a left from the goal state, you basically goes to again a non-goal state. Okay, so this is how you basically model a grid world. Okay, and the transition would be similar to what we do in the MRP. So let's see. My classical state representation is what? Is this basically, let's say I am in the 0th state, so it will be 0, 1, 0, 0, this one, right? So what is its shape? Its shape is 1 cross S, right? So you translate, and based on the action, let's say I took the up action, okay? So based on the action, I will slice the particular sub transition dynamics for that up call. That would be put in here. So that's an S cross S for the up call, right? Up action, S cross S. So you get a 1 cross S transition probability vector. 1 cross S transition probability vector, or you, let's say, what are the probabilities for 0? You will get 0, 1, 0. So you will surely transition to the next state. Okay, and this is a completely deterministic world. See, everything is 1 only, right? The probabilities are only 1. So wherever you want to go, you go there. There is no dynamicity in the environment. Because see, even if you sample from this distribution, you will always sample state 2 or let's say state 1, right? That's why it's a very uh, deterministic environment, right? So basically, the mouse wherever he wants to go, he'll go there. There is no stochastic theme in the environment now. Now, sometimes there is a concept called slip. Okay, so we'll not consider slip now. Slip means, let's say I want to go forward, but because the tile is slippery, I slip and go to the left direction. Okay, so you can always define a slip. Let's say there is a 20% slip in the environment. That means with 20% probability, you will not take the action what you are desiring to take. So basically, it's a slip in the tile. So you try to go forward, you slip and let's say go rightward or leftward or backward, something like this. Okay, so let's say even if this transition would have a high probability, 1 probability of reaching here, it will factor into 0.8, and then 0.2 would be factored into all the other directions. So if I do 0.2 into 2 divided by 3, it will be around 0.06, right? So all these direction would have 0.06 probabilities. So that's called a slip in the environment. But let's not model it for now. We'll assume that the world is a deterministic world. Okay, and how do you get the rewards? So this is how you transition to the next state, right? You just multiply the current classical state representation with the corresponding action matrix, you get a next state transition, and then you do a sample, you get the next state. What will be the reward? Reward would be what? From a current state, whichever action you took, and it's the same thing, 1, 0, 0. Let's say this is the current state, right? And you take the corresponding action matrix. So let's say this one. This is the up one, up. Sorry, scroll down. Yes. So you take the up sample. This is -1 plus 100, and so after multiplying these two, you get a -1. Why? Because you basically transition to here, and you get a -1. Okay. Similarly, if I am in the first state and I took right, I should get a plus 100. So if my current state is 1, so 0, 1, 0, and my action is right, what is the right matrix? -1, 100, 100, right? So after multiplying these two, you will get 100, this one, plus 100. You see, this is how the uh, thing works. So let's model it now. Let's code. We know all the details with us. We have all the details with us to kind of code it. Okay, and we'll see, we'll keep this thing in our this image in our code template, this image, and we'll try to play. We will provide the action, and we'll see whether the model is working based on this modeling. Okay, so let's just take a screenshot of this. This is our model. Yes, and we try to upload it here. mb.png, width can be 500 pixel, and then you do markdown. Yes, so this is our world. Okay, so we want to see whether after coding the environment, if we take action from like a starting state or any state, we'll see whether the world works as we intended to. Okay? So let's define s is equal to what? 0, 1, 2, action is equal to 0, 1, 2, 3. Reward matrix, we'll take it from here. I'll maybe move this to my other desktop and copy it. Yes, so the reward dynamics looks like this. It's an np.array of column vectors, right? So this is one column vector, comma, this is for up. Okay, this is for up. This is for right. This is for down. For left, and the values I can just directly put it from our like the previous drawing, right? It can be plus 100, this is minus 1, plus 100, plus 100. For down it's minus 1, minus 1, plus 100, and this minus 1, minus 1, minus 1. These are reward, and what is the dimension? If I check, it's like 4 cross 3 cross 1, right, as we intended to. Okay, now the probability transition dynamics, PTR. It's also an NP array, and we're basically just putting the thing that we wrote there to a code. Okay, so now it should have a 3 cross 3 matrix on its own. So this is one column, one row, second row, third row, and the matrices initially, let's say, have all of them can have zeros. Just put them with ones whenever it's required. So this is for the up call, right? This is for up right. This is for down, and this is for left. Up, right, left, right. Now probabilities would be, I'll just take it from the thing that we already did. These are the sorry, these are the probabilities for up. These are the probabilities for right. These are the probabilities for down. And finally, we have for left is this, right? Now, if I run this, and let's have gamma as a like a scalar value 0.9. When we don't care about gamma for now, it will be used for theoretical understanding or theoretical analysis of the environment. Okay, so we have all the things that we need: SAR, PTR, and gamma. 5 things. Now if I run, R shape is this and PTR shape is PTR shape. It's also A cross S cross S. Okay, now we want to code the transition and the reward thing. So let's say we want to take some action. Okay, so and So we need to have so as humans we are more comfortable with up, down, left, right? And the system takes in, like currently the system takes in actions as 0, 1, 2, 3. So we should have a mapping from human to system. So action map, what is it? Up, right, down, and left. And the action maps are this maps to 0, right maps to 1, down maps to 2, and left maps to 3. Okay. Now let's write the like there should be another function that takes in state ID and transition to a classical state, right? So def state ID to classical. State ID can be 0, 1, 2, right? So we can directly return. So I'll not, you can use a function called pd.dummies, but let's not use it. Let's just do an if else logic there. So if, so we'll do an if else logic. If SID is equal to 0, because there are only 3 states. Elif SID is equal to 1, else, or elif SID is equal to 2. So my state representation would always be a NP array of 0, 0, 0. Now based on the ID, we'll change that particular probability. Oh, actually we don't need to do an if else. We can just do SID state SID is equal to 1, right? And return state. So state ID to classical. If I pass 0, it will give me this. If I pass 1, it will give me this. If I pass 2, it will give me this. Okay, we are fine. Now to transition, we need to go with a start state first. So there has to be a start state. Start state, let's say start state is always 0. Okay. Now current state is equal to what? To get the start state, push it there and you're in the current state. Now while true, let's say I want to or while or let's say while true only, no worries, true, while true, and we'll also track the total reward. Okay, so while true, what we will do, we'll first, the current state is already in the classical state, so we can put it inside here, no, outside only. Okay, current state. Then based on the action, we have to query the action from the user, right? So input, please, here we can say I'm just doing some kind of a implementation improvement. Current state array. So in input, we'll ask you are in what state ID. Okay, so state, current state, you are in current state, action possible are up, or here it's like give action, and these are the possible action we also provide: up, up, right, down, left. And then user, if the user give the action, when you do current action is equal to an integer of what the person gives, like it's a string usually, right, in Python. So you get the current action. Now we can take out the matrix. So let's say PTR, right? PTR is like a big matrix. Now if I want to take out, the particular matrix for up, I can just do a indexing on up, and this is the up matrix. You can check it actually, PTR, PTR. This is the matrix we want, right? So this is the up matrix. So this is how we can take out the up matrix. Now the reward function also looks same. So reward, it's this. If I just want to take the up, this one, I can just do a 0, and this is the up matrix, right? So here we are providing URL DL like in a string. So we need to map it. We need to pass it to the action map instead of integer casting. So that gives us the current action map, a current action in numerics, right? Now we can sliced or action transition. Action PTR is what? Your PTR, and you take the current action. This is your current action probability, and reward action reward is also action R is what? Reward. You get the current action. Now we can do the transition. So here we have the transition of the world of the MDP. So what we will do, we'll basically do next prob, next state prob, next state probabilities are what? You just multiply the current state array, maximal current state array with the action PTR, right? Whatever action you took. And actually what people do, people actually do not make these two things separately computed. We just pass the entire thing here. That makes more sense. Okay, so let's not have two other variables. This is the next probability distribution, and to get the next state from there, what you do is just do a np dot random choice. And A is what? A is your state, this array of states, right? 0, 1, 2, and the probabilities are E is equal to next state probabilities. You get a state, let's say you get to state 2, right? Now you need to update the current state with the next state. I mean, you are in the next state, so in the next run, that current state, the 2 state will be the current state array. Okay, and also we need to, this is how we can get the next state, right? Now it will be also printed over here when we will be trying to take action, right? Now we need to print the reward also, right? So reward, we get it from here. So here we'll compute the reward. Reward will be same, a matrix multiplication of the current state array to the R current R. We don't need to also track this action R current. So this gives me next reward, or reward basically, a current reward, or let's write it as reward only. And we can do a sum. Where in current state this, we can do a print current reward is your reward, and then total reward that you've seen so far and with the total reward. Okay, and before adding the total reward, we just add it to the reward. So every time this total reward tracks in the total reward that you have seen so far. Now we just do formatting here. So what it should do, we start with the current state, right? With current state is 0. It should give us an action to act on that world. So let's run it. You are in state 0, you do right action should lead me to a wall, right? So you are again in state 0 and get a -1. So just for more, we can take this image from here and also have it over here. Right, so if I zoom out a bit, then you will be able to see. Let's interrupt this for now. Now if I run, we are starting from state 0, so we are here, right? Now if I do a down operation, it should hit the wall and come back to the same 0th state. If I do a down operation, it goes to the current reward is -1, total reward is also -1, right? Maybe we need to fix one thing here over here. Okay, this should be a 0 colon here. Okay, we interrupt. Yeah, same thing. A down operation here would give me the same state. My total reward, current reward is -1 as well as my total reward is -1. Now if I do an up operation, go up, that's what is the best thing to do at z 0. It takes me to state 1. My total reward is -2 now, and my current reward becomes -1. Good. Now again, if I do a left, that's not a good thing to do. It will again hit a wall. Left, it's in the same state. It gets a -1, so the total reward is -3. Now we are still in the one state, right? Now if I do a down, I will go back and come to the 0th state. Where if I do a right, you see, it goes to the goal state and the current reward it observed is 100. Okay, so this is how you can, and you can basically try out things. So if I, let's say I am actually here, right? Now if I do a left again, let's go back to state 0. So if I do a left, I'll go back to state 1. If I do a down, I'll go back to state 0. Okay, and let's see, if I want to hit the right side wall, I can take a right, get a -1 and also hit a, and again basically loop back to the same state 0. And my total reward, because I have once reached the goal state, it's actually 94. Now if I again want to reach the goal state, I will take an up and a right. I'm in the goal state and the current reward is 100, total reward is 193. Okay, so this is how you can code a grid world. Okay, so cell here. Yes. Any questions? So the while loop breaks every time it requires an input, and after each next. So the while loop breaks every time it requires an input, that is after each round. No, it doesn't break. So in the code, this input call in Python, it's basically a scanf operation in C. Okay, so the while loop doesn't break. You can interact in the world as long as you want. You need to, every time you need, like we need to give the action. So we are basically acting as agents here. Okay, so what we want in RL, that instead of us, an agent would interact in the environment and learn this policy. So what is the best policy? What is the best reward that I can get from the environment is if I take an up and if I take a right. So the best reward I can get is 99, right? So we should be able to find this policy up, right? Uh, that basically it. So the RL algorithm should be able to find what action is the best action. So up and right is the best action to reach to the goal state. Okay, and here the while loops is just continuing as long as you don't interrupt. this input state is actually asking us for the policy or for the state to action mappings. Later on, an agent will do that for us. Okay, no, not an LLM agent, by the way. Uh, it's an RL agent. Okay. So this is this part we did, right? The MDP. So how to code an MDP. Now we have enough ground. Like I guess you now know how to build these worlds, and this is the foundation of reinforcement. So let's just go over into a bit more theoretical aspects of reinforcement and see how it is, like how different type of algorithms are clustered. Okay, so we'll go back here to yeah, okay. Okay, so what we did till now was see how to like design the worlds, okay, where the agents would, or the RL agents algorithms would interact. So the general agent world, this does some kind of an action by observing some kind of state and some kind of a reward, right? Now these are timed. Why? Because it observes st, it observes st at t, it acts with at, and then at the next step it gets st plus 1 and rt plus 1. This is the entire RL loop, right? So what we observed till now is how to model this, right? You now know how the transitions works. If I need to design a grid world, how I can design it. So instead of designing it like this, if I have enough time, I can design a 10 by 10 grid, put the block state, put the goal states, and I can write the entire probability dynamics like that. So to do that, we actually have a really good tool. We can do it actually, but we will not do it like on our own. Instead, we will use a library, grid world. Okay, if I import this library, this small grid world library, yes. So in a stochastic environment, the only change in coding will be the PTR matrix. Yes, we'll describe a deterministic instead of deterministic system. That it will be a, and reward vector R will be random or bounded for each state. No, the reward matrix doesn't have any problem. Like it's basically state to action, right? If you take a action in a state, where you land. So so in a stochastic environment, where you land is actually dependent on the stochasticity, right? So now your uh, reward function can be also modeled as state cross action thing. Okay, so yeah, so let's see. Anyway, so for a stochastic environment, only thing the slip computation will be there. So there will be a non-zero probability in all the zeros. Okay, so let's define an environment with grid world. From grid world, import grid world, and this is a very kind of useful library. Okay, which I developed during my BTech. So yeah, so this has all the things that you need. It's a deep reinforcement library, it's a classical reinforcement library, everything you need for grid worlds only is there. So see, it expects a world string, like a slip. So you don't have to go and manually like compute those slip things. You can pass a slip probability that with 20% probability the intended action is not taken. Log false is fine. Maximum episode steps, how many maximum steps you want to take in the environment, These are the deep reinforcement. This block size is DRL, view size, random state, all these are deep reinforcement thing. Okay. So for classical reinforcement, we'll only talk about these things. Okay. Yes. And I'll explain, like right after this, I'll explain what do I mean by classical reinforcement, deep reinforcement and stuff. Okay. So this world. So if I go to the grid world library, there is a pattern that we follow to create this grid world library, okay, to create these environments, and this is the pattern. So I can just copy this pattern, pass that one here, and that would create a world for me. This is the environment. Okay, and if I want to do a show, missing policy. Okay, so let's see what are the things. Play as human. See this function, play as human. So what the thing that we did here, it's like very, like, it's mostly UL, all these actions, right? These are not really helpful. Like as humans, we should be able to interact it like this way. So yeah, here. Okay, and log is false. So if I do log equal to true, it actually logs the state transitions. Yeah, these are the different states, I guess. No, yes. Okay, so this is the grid world environment. Now, if I want to make a bigger environment, and these are the state transitions, you see. So at the end, we get to a goal state. Okay, and these are all possible states. So currently, the world has, instead of 3 states earlier, what we manually did, it has around 73. Let me do a number of state calls. So environment dot state count. This variable tracks the state. There are total 74 states. So you can assume 74 state, and your action are 4. What should be the dynamic size? It will be 4 cross 74 cross 74, right? We can check it. We can check it like this. And our sleep is 0.2. So it's not a deterministic world, it's a stochastic world. Environment.psas. The ptr variable is named as psas, and this is the exact shape. So instead of a cross s cross, so instead of a cross s, it is named as s cross, or I think it is still the same shape. Let's say, yeah, no, it's actually s cross a cross s, and this will be actually helpful later on. For the theoretical analysis, this shape is more helpful than this one. Okay, so you can check the dynamics like this. These are the dynamics, and see, there is because there is this 0.133, right? It's actually the sleep thing, and 0.8 is where the action should actually take you when it's a deterministic world. Similarly, I can also check RSA. Its shape is RSA dot shape, not SA. Yes, it's a shape of S cross A. S cross A. So only the shapes are a little bit different, but the matrices are there. So you can access to the RSA matrix like this. Okay, so let's say if I want to make a more a bigger world, right? I can go here. Let's take another world. Examples. Wait 1 minute. Okay. Here library or not here maybe. I want to just go for a bigger world. So this should be in the examples only. Environment. Yes, great environment, right? And now this is the big world. See, just copy the entire string and you can write your own string. So if you want, you can make your own uh, grid world models just by just writing this pattern. So now it's a very big world, right? And see, this is the agent. A is the agent, W are the wall, O are the whole states, or where basically the environment would get a very negative reward. And this is the goal state, this is the goal region. So there is a lot of food here. So the agent should find a way to avoid these whole states, dodge these walls and come to here. Okay. So if I just run this and play as human, uh, oh sorry, start. I didn't change the big world thing. Instead of world, this is big world. And this is the world, and this is like a very big world. It doesn't fit, right? Yes, it doesn't fit. So let me see whether I can. Oh, it doesn't fit my computer screen. It's actually very big. If I go, anyway, you get the point. Yeah, this is like this big. You see? Okay. Uh, can restart. Now, instead of hand coding all these things, we can use the grid world library to code to kind of model the world for us. Okay. I missed something here. What are these symbols? WG. Yes. So to define this world, we use this W as wall. Okay. A for agent, O for goal, like whole states, where the environment would basically give you a very negative reward, and then G at the goal state. So a better starting state will be a starting model will be this, a small model rather than a very big one. This O are the whole states and A is the agent and G is the goal state, right? So now if I run this, it actually built an environment like this. Now if I close this and change the world representation, instead of G state here, I put the G state here. Now you see the location of the cheese would be different. And now the cheese is here. Okay. Okay. So let's not go into this how to define a complicated wall wherein there are multiple level of O's. Multiple level of O's mean. Can you elaborate on that? Multiple level of O's means like there are like
So O here refers to the old state, and what if there are multiple number of the old states like O1, O2, O3,
yes. So you
etc.
base
And
so do you want to kind of differentiate it based on the reward function that one O1 gets minus 100, O2 gets minus 200 like this?
yes, yes, true, true.
Yes, so this library doesn't support that. Maybe I can add that feature later on. But here these O's are actually all minus 100. So it can be done. It's a very good suggestion. I would add the feature later on maybe that you can define different degree of whole state. So and the point is so So the whole states are where the so see in the here, right? These are actually traps. So ideally the mouse should go and die there. Okay. So that's why you put a -100 there, and the environment would basically close off. Okay. However, if we want, we can also add different degree of holes. It's a it's a very good suggestion to yeah, basically it's different reward different penalties for how the mouse would die, right? So I maintain the grid wall library, so it's my library. Okay, you can find it in my GitHub here. Here, and this library is really useful for us to actually like play out with different algorithms. Don't have to define all the worlds. um, how does this algorithm learns? So it doesn't learn. So still now we are only building this world. Okay, and now just right now what I showed you is a convenient way to define a world. So you will get the what are the things that you are required to define a world. So you just saw, right, how we define the grid world for us. We from this world we need five things: S, A, R, probability, and then gamma. Gamma still you don't like, we don't discuss gamma yet. We only like define these variables by our own, and then we put gamma equal to 0.9 for now, right? So the grid world library gives you a very convenient way to define this SARP by just using a instead of hand like computing everything by hand, you can just write this string pattern where W means wall, A means agent, G means goal, and O means whole state. You basically can define a world very easily. Okay, so now output. So the output reflected your movement in the Pygame. Yes, yes. Say the output you see the rendering thing. It's actually in Pygame. Okay, thank you. So yeah. So now what we learned till now is we can model and Markov process. We can model and Markov reward process, and we can model a Markov decision process. Right? Now is the best time to to classify or kind of group RL algorithms for now. Okay. So this is RL. Okay. Now there are two subgroups called classical and deep. Okay. Deep RL, classical RL and deep RL. Again, this classical RL can be categorized into two: model based, model free. And finally, this deep RL has only one category, it is model free. Okay, model free. So what are these things? So classical RL has another name called tabular RL, a table based RL. Okay, table based. Now what these things mean? So this model thing, right, this model keyword actually means the model of the world. This is known as the model. Models. So the general thing is in RL, this classical table based RL means classical. So these are like very useful theoretical concepts. Okay, and most of the like short questions, if they comes, it will come from here. So classical RL. So classical RL means the state and the action, both of them are finite. Finite. So there is a finite number of states and there is a finite number of actions. And so classical RL means only this. Within it, you have a two separate things, right? This model based and model free. So what does these two mean? So model based mean when you have access to the P and the R. So when you have access to the probability transition dynamics and the reward dynamics, that's a model based classical reinforcement learning. Okay, and the state and action space are finite. That's why you can access the P and R, right? Because if these are infinite, then the matrices will be infinite, right? Model free in classical means why there is no deep MBRL? Wouldn't Dreamer consider deep MBRL? Yes. So this MBRL everything they comes under the yes, model based reinforcement learning is there, but so what they do, they don't have access to the world. They build a proxy to the world. Okay. So what they do, they, for example, it's applicable only to few domains. Let's say it's a very easy thing to uh, model a chess game, right? So in that case, if you want a deep reinforcement learning algorithm on a chess game, you can kind of consider it as a model based deep reinforcement learning. But in most scenarios, this when deep reinforcement learning is applied, right, the state space or the action space is infinite. So this dreamer or this AlphaGo or the chess playing agent, right, all these things are special cases where the environment has a very large action space or a very large state space. Okay, but it cannot be tractable in a table. It can be only tractable in a neural network. That's why you can have a kind of a hybrid thing, but it's not applicable widely. Okay, it's not really applicable in all cases. So there are few scenarios where there is a like the state space can be very huge, but it's finite. So you can go with a model, and you can also model the environment efficiently. Then you can go with a model based deep reinforcement learning. But generally, it's not the case. Okay. So yeah, there are some. Let's just add it with a blue color model based DRL. Okay, we'll maybe cover it later on. Okay, so the classical, what is the catch? Classical has a finite state and action. So let's say there are 500 states and 4 actions. That's the classical classical world. Okay, and now if you have access to the probability transition dynamics and the reward dynamics, that's a model based. And if you don't have access to these two things, instead you have a way to interact in the model. Interact. So you basically can interact in the environment infinitely as you want. So uh, what does change from here to here is model based means you know everything about the world. You know how, if I take this, what is the transition from state 0 to state 1? You know every probability, everything. Now in model free, you can act infinitely long, right? Without any consequences. So you have basically a digital twin of the world that you want to learn, and then you can act infinitely long, but you don't have direct access to the probability and reward dynamics. So uh, yeah, and also the state and action are still finite. So probability, reward, you don't have access to them, but you can have access to an interact method. Okay, and that is also there in the grid world package. So if you go to this, and this is how you can basically this is some algorithm we'll discuss later on. This is value iteration. So you can access to PT like P R matrices. So these are model based methods Whereas if you want, you can also consider accessing the step method, environment.step. It will give you an access to interact in the environment. So value iteration is a later algorithm. It's a dynamic programming algorithm we have later on. So let's not worry about value iteration for now. Okay, we first need to cover what is value, what is reward, what is return, all those like theoretical concepts. Okay, so there are two methods. So one is this: you access directly this PES everything from the read world library or from any model that you have developed, or you can directly act with it. So environment.step, and this is an API that everybody uses. So OpenAI or any other third-party like reinforcement learning library, right? They all use this step function to interact in the world. Okay, so you'll see there are a lot of environments, like let's say OpenAI Gym, right? OpenAI Gym. This not this one. This, right? And it has wait, there was a site. Uh, Maybe this one. Oh, images would be good. Yes, these are all open. These are see, these are all different environments. Yes, gymnasium. Yes, these are all different environments that you can access and have the same interaction method. Environment.step. Okay. Now let's go back to this thing. Okay. So classical, what does it mean? It has finite number of states and finite number of action. Model free means, sorry, model based means you have access to the P and R matrix, and model free means you can interact in the environment as long as you want, but you cannot have access to the P and R. Okay. Now that is the general use case, right? You cannot model how a quadruped robot would work in the in general terrain, right? You cannot model it. It's a infinitely long state space, right? So in most RL scenarios, it's model free. Now,
Sir, reward will be by us, right? We
reward
we
would,
will know the reward because we are the ones who are giving the rewards.
yes, yes.
So reward is finite. Can we consider reward as finite?
No, see, reward matrix, the size of the matrices were like this. Yes, the probability matrix has a size of S cross A cross S, right? And the
Yes.
reward matrix has a size of S cross A. So if the number of states are infinite, then the reward matrix is itself an infinite,
Okay.
right? And same, the number of states, if it is infinite, so for example, if my state representation is basically torque values in the motor, right, of a hand, let's say there is a mechanical hand and we want to pick up some object from the table, and the state representation is basically the torque that the sensors are observing in each joint, then the torque value is a real number. Real number can have infinite possibilities. Let's say it is only, let's say 4 joints are there, so 4 joints means 4 torque values. So the state space can have infinitely possible unique values, right? So that's why the state space, like currently we are representing at 1 0 2 3 like this. Usually it is represented as let's say a vector or something, and this possible number of vectors are infinite. So your P and R for a for a deep reinforcement scenario is an infinitely long table. You cannot track it in memory.
Okay. Since it is continuous, then but in such a case of robotic manipulation and all, once the
Yes,
task is completed, at the end of the task, we will provide a reward.
yes.
Uh,
Either you can also model a reward based. Let's say the task objective is a very high reward. Let's say you, whenever the task is complete, you can put a +100, right? But you can also have a small reward component to make the arm move in a smooth way. So you don't want to have very much vibration in the motors, right? So you can basically have a penalty like minus of vibration in the reward called. So that would try to minimize the vibration in the motors and try to achieve the same goal. So this type of
Okay.
small reward modeling is there. So later on, you will see when you actually engineer a reward function for a environment you want to solve, you have to take into consideration all these small details. So let's say I don't want my machine to vibrate too much, so I will have a penalty about vibration. I want to make it take a particular style of action. Let's say I only want to make it move in a like instead of a continuous motion, I want to move it in a since edit distance motion, right, or a some particular geometric pattern. I can have penalties if it breaks that pattern.
Okay.
Yes. Wait. Okay. So now I guess you understand what this classical reinforcement. Only thing is you have S and A as finite, and deep reinforcement is when the S and A are continuous. Any of them are continuous. So there are scenarios, for example, this DQN algorithm, right? It works with a continuous state space, but with a finite action space. Yes. So model free environment is what we have been seeing till now. Week 1 and week 2 to estimators algorithm and Q estimator find optimal R. Yes, exactly. So there are algorithms like DQN which works on a continuous action space but a finite state space. Sorry, continuous state space but a finite action space. Yes, continuous. What would be an example of having continuous state and or action? So see, you can have three or four different example. State, action, right? So it can be finite, finite, finite. Sorry, continuous, finite, mm, finite, continuous, continuous, continuous. So example, we'll see the examples later on. What are the settings? So if they are finite, this is basically you can RL setting. Okay, so the RL setting, finite, it's a model based method. Okay, now continuous finite, it's a you cannot see if it is a continuous in any of the axis, you cannot model it, you cannot track it, right, in a memory. So the PTR and RTR, it's not tractable in memory, right? So that means it has to be a model free method. It's a model free method. You can interact, you can develop the interaction method, but you cannot actually like store the entire PTR and RTR matrix in memory because they are dependent on the size of the state, right? So P has a shape of S cross A cross S and R has a shape of S cross A. So if the S is continuous, it's basically infinite number of possibilities. So the table would be so large or basically infinitely large, right? Now here also it's a model free method because action space is infinite. So these two will be infinite, right? And this is obviously a model free method. Now an example, and because these are continuous, right? So this can be modeled as a classical reinforcement. All of other things can be only modeled as a deep reinforcement problem. Okay. Example, a finite to finite grid world, right? Now classical to sorry, not classical, continuous to finite. State space is continuous, action space is finite. What is uh, example? Pole balance. So your state can be basically the angle of the pole, right? And then you can basically balance it with left and right. So pole balance. Now the state space is finite, action space is continuous, right? Uh, State space is finite, action space is continuous. Um, let's say indoor navigation. Why? Indoor navigator robot. It sees the environment as a pixelated frame, right? So pixels, let's say my resolution is 256. No, let's say my resolution is 480, 480 cross 480, right? The camera resolution, and there are 3 channels, and each channel can have these are the number of total pixels, and each channel can have 256 values, because it's like each bit is like each pixel is represented, or the RGB values are represented as 1 bit, sorry, 1 byte, right? So the possible number of states are 256 to the power this, right? So it's still finite. It's still finite, but it's very large, right? So indoor navigation is a finite state space and continuous action. Why continuous action? Because the robot needs to maintain the torque of different wheels, right? So that's the continuous action space. Now continuous can be, let's say, training a quadruped or training a anything. So instead of the indoor navigation from a camera, if we just switch to sensor indoor navigation, right? That also gives me a continuous to continuous. So the sensor values are real numbers. It can change into continuous, like it's basically infinite number of possible sensor values. So the state space can be continuous and the action space is already continuous. Got it? So any questions from here? Okay. So this is the your uh, different RL um, algorithms based on how much you know about the environment. And see that classification is only based on how much you know about the environment. It's not about the algorithm. Algorithms comes after the environment. Okay. 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 So what we covered till here. Here now that should be some. Now we need to analyze these environments. Okay. So after we now have enough background to code these environments, but there are some theoretical concepts we need to know to analyze these environments. So we'll see it one by one. And from now the algorithm part starts. Okay. So how we can solve the environments actually. Okay. So in Markov process there is please mention resources to learn easily. So you can, okay. So the easiest way to learn this is to ask questions in the sessions. Okay. If you think some part is you are confused about some part, you can ask, because resources you can only read them or listen to them. You cannot cross query, right, at this point. So try being as vocal as possible during the sessions, and the resources I will provide anyway. So there are some books also. I'll send the links of those books like Sutton Barto and other books which covers these processes and these algorithms in a great detail. Okay. So where is the learning in deep RL in the sense of deep learning wherein features are automatically extracted? Okay. So to answer this, actually, like as we move around the course, it will be more clear where the learning comes. Um, so in classical reinforcement, when things are tractable in a table, right? That's why it will call the table-based RL method. You will see we are basically doing a dynamic programming thing. We are updating a table based on what we observe in the environment. Okay, so the table is our learned parameter. Now, whenever my state or action, so you can think of it like this. So let's say this is my state and this is my action, and these are finite. So it's a grid, okay, of learned values, and the values represent how much a particular state is beneficial for me to take some particular action. Okay, so let's take our same grid world example that we coded. State 0, state 1, state 2. This is up, right, down, left, right? So if I just select this table and move it up, from here to here, right? Yes. So now tell me, for high, low, and medium values, which values will be high? So this represents how much a state is good or bad, state and action is good or bad. So let's just only write good and bad. Okay. So state 0, action up. Is it good or bad? Good, right? We are going closer to the cake or the cheese. So this is good. Now from state 0, taking action right is bad because you basically self loop and get -1. Here also you get a -1, but it gets you closer to the goal state. That's important. So you might get a instant reward as negative, but in future that leads to a positive reward. This is where the notion of return comes. So even if the current reward is -1, the return is higher than other actions. So let's just try to see from one step. Okay, so the up action is good, the right action is bad, the down action is also bad, the left action is also bad. Now from state 1, if I take up, it's bad. If I take right, it's good. If I take down, it's bad. If I take left, it's bad. Yes, but as far as the algo is concerned, what is the good or bad? Do we impose some box metric of some sort, or also account for less bad? Yes, yes. So that's the return. That's the return. I'm basically going to that logic of a return. Okay. Okay. Now in second state, we go to up. It's okay. It's good, right? Good. We go to right. It's good. We go to down. It's good. We go to left. It's bad. Right? So this is the learned thing. Learned. Right? And it's actually known as a Q table. Okay. So, so in a case where the state space is finite and the action space is finite, this table is tractable, right? Now, in a case where one of them are infinite, basically instead of a, so it's like this: you have an axis which is infinite long, and then you can have 1, 2, 3, 4, 4 action: up, down, left, right. Now to learn this, a table is not, it doesn't make sense, right? So instead, learning a plane makes sense because this entire thing is continuous, right? Here learning in a table makes sense. The up one, sorry, this one, but for a continuous state space thing, it's mostly a table. So if this is the state and this is the action, there are 4 points that we know. Now it basically learns a table. Instead of a table, it learns a plane, some kind of a metafold. Okay, and that plane is the neural network. Okay, so what does it mean? So it's a function from state to action values. Say your, it's known actually as QSA, QSA1, QSA2, QSA3, and QSA4. Yes, this is what you learn as a neural network. Yeah, so if it is if it is only two things, right, good and bad, then it can be a classifier. But it's not usually good and bad, right? It's a degree of good and bad. So it's a regression task in a sense. So yeah, you can think of it as if the states are classified into only two type of categories, good and bad, then it's also only a classification. But usually it's a degree of goodness or badness, and that goodness or badness is measured by return. So we'll now look into how return is computed. Okay. So now this thing is clear, right? That what the neural network learns in a case where one of the s or a is infinite, it learns a plane instead of a table. So let's say here, if I want to check whether my taking action right is good or bad, I can just do a indexing, right? But for a neural network, I need to basically query the neural network with a particular state value. It will give me access to all the q values in that, the intersect of q values in that plane. Okay, and if I check for a particular q value, I can also query that, and then I get this point QSA 1, let's say. Yes, the loss function, everything will cover it later on. Don't hurry too much. Let's build up the foundational concepts first. So now we know that the state can be good or bad, but usually it is a degree. It's a scalar thing. It can be very good, very bad, middle good, not that good, not that bad, something like this, right? So it's a continuous scale. So how to measure this goodness of a state? This is called return. So total reward doesn't give me any anything by which we can identify whether a state is good or bad, right? It just, the total reward can only give me whether the entire sequence of action and the state I have visited is good or bad. If it is good, then I will get a very good total reward. If it is bad, the entire sequence is bad, then I will get a very bad total reward, right? But how, like, we cannot identify whether a particular state is good or bad, or a particular state action is good or bad by total reward. Okay, so let's go into that. I think these queries are now much clearer, right? What a neural network learns and what does a tabular method fails. When does a tabular method fails? Yes, so I think we have 5 more minutes. Anyway, so we'll try introducing to these concepts once. One is called return. What does return means? It's okay. So return, let's see a concept of a return. It's, the symbol is GT, G capital T. Okay, why T? T is the time step. So let's say you start with S0, right? This is the starting state, and then you transition to S1. Then, and we are talking about a Markov reward process now. There is no action. So we only want to check whether a state is good or bad. Okay, we don't want to check whether a state is good or bad given this action. Okay, we only want to the transitions are automatically happening, but we only want to check whether a particular state is good or bad based on the reward we are seeing. So from S0 we get R0, from S1 we get R1, then transition to the next state S2, we get R2, then transition to ST. Basically you get a transition dot 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 here, dot dot dot, right? And then finally you transition to ST and you get RT. Again you transition to ST plus 1, you get RT plus 1, and finally dot 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 you get transition to a terminal state capital ST. Okay, it can be an inter. So there is another classification of a finite horizon environment and an infinitely horizon environment. Okay, so a finite horizon environment, this T is finite. So basically it will end, the environment will end after some time. But in an infinitely horizon infinitely, or basically infinite, yeah, infinite horizon environment, you can think that this T goes to infinity. So basically T is equal to infinity. You can transition as long as you want. Okay, and these finite environments are also known as episodic environment. So basically there is an episode, after that it will end. Again the new, and you need to, if you need to let's say play in the environment, you need to again start with the starting state. Okay, it will end, terminate somewhere in an episodic setting. So now return is, now see, this is the instantaneous reward, right? R0, R1, R2, R3, all these are instantaneous rewards. Okay, now what does total reward means? Total reward is R capital T is equal to R0 plus R1 plus R2 plus plus dot 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 plus RT plus RT plus 1 plus dot dot dot. Here also you get some reward, right? R capital T plus R capital T. This is your total reward. Now return, so this doesn't say anything about your state, whether the state is good or bad. So what return tells you, basically it tells you whether the entire sequence is good or bad, right? So return at capital T tells you the cumulative reward that you see from here to the end, the total reward from here to end. That's it. That's the fundamental concept of a return. So from ST, capital ST, it's termed as GT. GT would be what? RT plus RT plus 1 plus RT plus 2 plus dot 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 plus R capital T. That's it. That's the concept of a return. So now if I know all the cumulative sums from all the states, I can see which state gives me more reward or more return, more total cumulative return. That gives me a kind of an estimate of how good or bad that state is. Okay, you get the kind of the concept, right? So return, so for let's say G0, G0 would be exactly as RT, right? Similarly, if I go for G1, it will be basically R1 plus R2 plus dot 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 R capital T. Now if I can write G1 would be R capital T minus R0, something like this. And this is later on you will see there is a concept called eligibility traces. All those things are like this type of formulation is there in that case, but it's not currently required. Yes, so this is known as a return. Now the problem is, it's very good, this formulation is very good for an episodic setting. It's not good. So basically what you do, you basically forward, like you do a forward loop to the end of the episode and see, okay, from this state how much cumulative return I am getting. Okay. Now, if the end is infinitely long, or the episode has a very long length, right? Yeah, but this is for a single realization of Markov chain, right? Yes, yes. The chain is large enough in a finite horizon, it might not even visit all states. For a different realization, GT might be different. Yes, yes, yes. So there is a concept of a value function. Value function is your estimation of GT. So that thing, right? So you might, like, the Tth timestamp total reward can be different for different unrolls. Okay. Yes. So your GT can be different. Okay. Uh, we'll see. No worries for now. Okay, so for an episodic setting, the GT is fine. For an infinitely long setting, so let's say a non-episodic setting, this would, even if the reward is +1 or -1, it will always saturate to +infinity or -infinity, right? Because it's non-episodic, it's infinitely long. The t is equal to infinity. So in that case, we come up with a new formulation of this discount factor. So earlier the formulation was plus RT plus 1 plus dot 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 plus R capital T. Now what we do, we multiply, let's write it another thing here, plus RT plus 2. What we do, we basically multiply, after the current step, we multiply everything with gamma's powers. So gamma, then second part will be gamma square. At the end, it will be gamma to the power t minus 1 or plus 1 basically. Okay, so this is known as discounted return. Discounted return. Okay, and why it is important is basically like this. Let's say I want to take some decision. So I have a mechanism to kind of see through the consequences of my decision in future, right? So this gamma factor controls how much future I want to see. Okay, so that's why even if in an non-episodic setting, when the t is infinitely long, it can bound the return to a particular a fixed number of future states. So for example, if the gamma equal to, and it's a decreasing series, right? So gamma, um, the powers of gamma are basically decreasing, so it's a decreasing series, gamma to the power n, right? If this is n, it's a very, like, it's not actually this shallow also. This, if this is n, gamma to the power n is basically a series that looks like this, based on different gamma values. So if gamma equal to, and this is like very close to 0, this is like very close to 0. Okay, mathematically, thus the addition of geometric coefficient given mod gamma is less than 1 for GT to be bounded in, yes, exactly. So it allows uh, the, the return computation to be bounded in the infinite horizon case. So for example, if gamma equal to 0.9, that means this this is the 0th line. Okay, so all the things, this is gamma to the power 11 will be very close to 0 actually. Gamma to the power 12 will be again very close to 0, but all the elements before it will be non-zero. So it's basically your exponential average logic. Okay, so if gamma equal to 0.9, that means you are summing next 10 steps. That's it. If gamma equal to 0.99, then you are averaging 100 steps into the future. And how it is computed is basically your number of steps can be computed as 1 over 1 minus gamma. Okay, so this is the number of steps the averaging would work. So if the gamma is 0.9, then the n becomes 10. If it is 0.99, it becomes 100. If it is 0.999, it will become 0. It become 1000, right? So this is how you can basically bound the return computation in an infinite horizon case. But for, yes, for an episodic setting, even if you keep gamma as 1, that also makes sense. And if you see if you just put gamma equal to 1, n becomes infinity, right? So basically you are summing across the all future states. Okay. Okay, so this is the concept of a return. Now we'll see, and like I guess you already mentioned, right, that there can be different GT states. So in different roles there can be different GT states. So we'll just discuss one quick equation that comes from that notion, and then we'll stop here today. So yes, and currently we are only talking about your uh, Markov reward process, right? So there is no action as such. And what, like, how we can represent that different, there can be different GTs in different run of the Markov chain is like this. So let's say we are at ST, okay, and based on the probability transitions you can transition to ST plus 1 dash. Quickly finish this and we will close today. So click ST plus 1 dash, it can be ST plus 1 double dash, it can be ST plus 1 triple dash, right? And let's say have dot dot dot, some many possible states. It can transition to all of them with some probability, right? So P S dash T plus 1 given S T, sorry, S T, this probability would be P of S double dash T plus 1 given S T, this probability would be S triple dash T plus 1 given S T, right? Now this path, and you will get a different rewards, right? At T plus 1 dash, at T plus 2 dash, at T plus, sorry, at T plus 1 double dash, double dash, triple dash, and here you get an RT, right? Now here also you can again transition to a set of different sets. Here also you can transition to a different sets. Here also you get transition to a different sets. Now say, let's say we are computing GTs, right? So in this path, if I traverse in this path, right, let's say my GT is GT dash. In this path, if I traverse, let's just color code it. Okay, if I traverse during this path, my return is GT double dash, and if I traverse in this path, my reward is GT triple dash, right? Now what is the GT here? So then the GT here would be an average of all of them, and now we know the probability of getting those GTs, right? So the probability of transition to this path is this, and the return is this. The probability of transition to this path is P of S double T prime GT and this, right? Now what is the GT here? Average GT. The S, you can basically see in different roles of the Markov chain, you will see different GTs, right? Because you transition to a different next state, right? But what is the average GT you are observing? The average would be basically a probabilistic sum of all the GTs, right? So the average GT, AVG GT, is what? Probability of S dash, sorry, S dash T plus 1 given ST times what is the GT here? GT dash plus probability of ST plus 1 dash dash ST GT double dash plus finally the probability of, and dot dot dot, all the other possibilities, plus ST plus 1 triple dash given ST GT triple dash. right? Yes, so in a setting where actions are involved in learning would be to pick the arm which maximizes the estimated GT. Yes, yes. So in an bandit algorithm, all right, in a bandit algorithm where you have only picking the arm as an action, you would pick the arm which maximize the average GT, not the instantaneous GT. Okay, and this average GT has a name. It's known as value function. Value function, and it is not a function of it's basically function of state v of st, right? So from st, whatever GT you observe, if you get a probabilistic sum of all of the GTs, you get a value of that state. So whether that state is good or whether the state is bad, right? Now see, there is a really good recursion to it. See here, if I know value of st plus 1, then I don't have to unroll here, right? If I know the value of st plus 1 here, I don't need to unroll from there. So basically s double prime, this is dash, this is double dash, and this is value of s triple dash t plus 1, then I don't have to unroll, right? So that gives us a really good recursion. So value of st is equal to current reward rt, sorry, rt plus what? Probability, and probability of what? Probability of s summation, probability of st plus 1 given st, and then their values, right? And this st plus 1 can be from a set of possible next states. This this is for a infinite, like for a finite horizon case. If I need to have the same reward, like this gamma factor, right, then I just multiply these with gamma, or let's just put the gamma in a different color just to factor in the discount. The next steps are discounted with gamma. You get a current reward, you transition to the next state, observe the corresponding value functions, and this gives me a recursion, right? So in matrix form, it is written as v is equal to r plus gamma pv. Okay, so if you have access to the r and v matrix, you can just have this recursion. And how we can solve it? You can just take it v minus gamma pv is equal to r, then I minus gamma p times v is equal to r, and finally v is equal to what? I minus gamma p inverse r. And this is an exact solution. If you have access to the p and r matrix, you can compute the value function of a particular MRP and see which state is good and which state is bad in a yes. And the in which state is good or which state is bad is dependent on what is the gamma factor. So if the gamma factor is 1, you are basically looking into infinite horizon case. So if you transition infinitely and see what is the good or what is the bad, or if you have gamma equal to 0.1 0.9, then it would be like what is the good or bad state in next 10 steps. If the gamma is 0.5, then what is the good state in next 2 steps. How do we know if I minus gamma p is invertible, right? So in most scenarios, what I have seen in so if the rank of the p matrix, right, if the rank of the p matrix is less than the order, then it is not invertible. Okay, so in most scenarios it will be invertible, but it doesn't work really well when there are lots of self loops. So if the environment is very constrained and it has lot of self loops, right, then it's a problem. It might not invert um, properly. Okay, and another thing, if the gamma is 1, then it is and the world is deterministic, then it will not invert. It will not invert really in most scenarios. Could you please repeat how do you classify into good or bad from the value function? Yes, so the value function is a continuous value. So it's like a score. It's like a score function. Okay. So if the value is, let's say, 1 and the value is of another state is 100, then you can directly tell this state is better with respect to this state 0, or with respect to any other state which has a lower value. Okay. Yes. So we can quickly do this inversion and see. Understood, right? So we can quickly do this inversion from our previous uh, process, this one. Yes, we have this reward process with us, right? And we have also the P and R matrices. So P and R matrices, I'll just copy them. And let's see the shapes. So what are the shapes? We need to invert it. So P is S cross S, and gamma is a scalar. I would be S cross S. So the inversion will be also S cross S, and value is for every state, right? Every state it should have a value. So it's basically an S cross 1 thing, right? So this R should be an S cross 1, so that after multiplying it, it will get an S cross 1. Okay, so we'll do the things accordingly. Let's see. So this is our reward process. Computing exact value function. Sorry. Yes. What is the transition probability dynamics? This one is the transition probability dynamics. Let's name it as P only. Oh, NP is not there, so import NP. What is the reward? Reward should be a straight cross 1, right? So it's an np dot array. So the first state has a C, V and S. So C has a 10 minus 1, 5. 10 minus 1, 5. Now our equation is what? To get V, we need to run V is equal to I minus gamma P V inverse R, inverse time R, right? Time R. So we'll do. So np dot I gives you the 3. There are 3 states, so it gives me the identity matrix. Okay, minus gamma. Let's keep gamma as 0.9. Okay, so we are basically identifying the goodness or badness of a state, of the state C, V, and S with by just observing next 10 transitions in the future. Okay, so gamma times PV. Uh, yes, so P np dot matmul P. Do we have T or no? Only the P, right? Not PV. Sorry, gamma P, and then we need an inverse. To take an inverse, we can do np dot linear alg dot inv, and there we have the inverse, right? And we can just then multiply it with the R matrix with an np dot matmul, and that gives us the V matrix. Oh, sorry, it should be comma. Okay, now this is the goodness or badness of a state. So if I just see, sorry, this image over here, zoom it out, right? So the chocolate state has a value of 48, the vanilla state a value of 24, and the strawberry state has a value of 38. Got it? So if I just unwind based on this MRP, in next in future next 10 steps, this is the returns, that this is the expected return that you will get from chocolate state, from vanilla state, and from strawberry state. Okay, so yeah, so we'll maybe revise these things again next week, because these concepts are really tricky to stay in your brain. So like once, like early when I read them first, it took me a while to actually consolidate them uh, in memory. So okay, I'm sorry, do we stay 10 step because the finite horizon is 10? No, because the gamma we took is 0.9. So if I take it 1, it's an infinite horizon thing. And if you check, this becomes unbounded, right? If I take gamma as 1, means we are taking the entire horizon, infinitely long horizon. These things become minus infinity. Why? Because it's an unbounded call. Let's say if I have, why it becomes minus infinity? Because there is a -1 number here. If all of them are positive, it becomes plus infinity. Oh, still it becomes minus infinity. Anyway, so yeah, yeah, you get right. So if the gamma is your 1, then we are basically looking into infinitely long horizon. So these values are unbounded. And if I have a 0.9, that means we are looking into only future next 10 steps. So it's now bounded. If I look into 100 steps, 0.99, it's bigger, right? Because we're looking into 100 steps now. The values are larger. Yeah, but the observation is still same. The chocolate is the highest rewarding state, then the strawberry, and then the vanilla. Even if I look for 100 steps, um, it's same, and we can actually verify it by looking into one step. So what is one step? One step would be taking it as 0, 0, 0, not 0.1, 0, right? See, this is the actual reward function, right? 10 minus 1, 5. If I take into 2 steps, that is 0.5, 0.5 is basically 2 steps. So 1 divided by 1 minus 0.5 is basically 1 divided by 0.5 is equal to 2, right? 2 steps give me a bit more information. Okay. Now if I go for 10 steps, 0.9 is the 10th step. It's more information, or basically you are looking into future even more. And if we go for 0.999, right, or 999, that means we are looking into 100, like, into 1000 future steps, 1000 future unrolls. You can, yeah, the values are larger, but the observation still remains almost similar, that the chocolate state is the highest rewarding state, then the vanilla state, sorry, then the strawberry state, and then the vanilla state. Okay, so this is known as the value function. Okay, and the value function is only defined for a Markov reward process where there is no action. You only unroll and, right, you only unroll and take the average of all the returns with the transitions. Okay, and this value state, when there is action also, is known as Q function. The value function is known as Q function when there is action. Oh, so formula for considering horizon formula is no. So let me do the thing. Horizon, how much horizon you are looking into? T. Oh, you are actually right. Yes, you are actually right. T is equal to 1 divided by 1 minus gamma. So if the gamma is 0.9, that means 1 divided by 0.1 is equal to 10. Okay. So okay, let's stop here. I think already have too many theoretical concepts today. So we also covered discount factor, value function, exact value function even, right? Um, yes. So next day we'll see how we can solve given this MRP yes, I'll recommend a book after this class, right? I'll send you a list of books that like actually the Soot and Barto reinforcement learning book is Introduction to Reinforcement Learning is a good book. I'll send you the links to the books after the call. Okay. So next day probably we'll do question answering sessions from week 1 as well as week 2 and like show you how you can solve given the current foundation that we have, right? How we can solve the grid world, any grid world which has a kind of a tractable number of policies, possible policies. So we'll see it the next week. From next week we'll try to solve the grid world environments. Okay, so till now we cannot solve them, right? We have to basically go and so like if it is a small environment we can go and like play our own and solve it, but from next class onwards we can actually solve them with the current foundation. Okay. Okay, so let's stop here. I'll stop recording.